Z-image, an efficient image generation foundation model with single-stream diffusion transformer. That's the title from the Alibaba Group team. And it contains a huge promise. If you're a researcher, an engineer, anyone really who's getting tired of this scale at all costs philosophy in text-to-image research, you really need to hear this, because Z-image, it fundamentally challenges that entire paradigm.
It really does. I mean, the top line numbers here are a massive departure from what we've come to expect as the industry standard for state-of-the-art performance. The Z-image team has achieved results that, frankly, rival top closed-source systems. But they did it with a model that's only 6 billion parameters.
6 billion! That's just it's tiny compared to the behemoths we see today. And this efficiency, it goes way beyond just the model size, right?
Precisely. We can actually put a dollar amount on it, which is pretty rare. The entire end-to-end training pipeline costs just 314,000 H800 GPU hours. At current market rates, that's what, roughly $630,000? To train a foundational model that performs at this level, it's incredible.
And then for deployment, for actual use, they've got Z-Image Turbo, an accelerated version that gets you sub-second inference in only 8 NFEs. And critically, this means it's accessible. It's compatible with consumer-grade hardware. We're talking less than 16 gigs of VRAM.
And the quality is there to back it up. Z-Image is really exceptional in its photorealism, and this is a big one, outstanding bilingual text rendering. It's reliable in both Chinese and English, which is an area where even huge models still really struggle.
So for today's analysis, our mission is to unpack the entire Z-image blueprint. How did they pull this off? How did they get elite, accessible performance without just throwing scale at the problem and without the shortcut of distilling synthetic data? Let's start by maybe setting the scene. What's the T2I landscape they're operating in?
Well, when you look at it, the whole environment is kind of split into two impractical extremes. On one side, you got the proprietary systems, the black boxes like Nano Banana Pro, Seadream 4.0. They're powerful, sure, but there's zero transparency, no access for research. They're commercially locked down.
And then on the open source side, the problem is just sheer size. You've got models like Hanyu on Image 3.0 at, 80 billion parameters? QuenImage is 20 billion. So even though they're technically open, their hardware requirements make them functionally impractical for most people.
Z-Image is proposing a third way. Their whole philosophy is efficiency through optimization across the entire system. That $628,000 price tag, that's not just a fun fact. It really underscores this deep commitment to efficiency. It's a move away from the old idea that you just have to burn more resources to get more performance.
And the tangible result of that is Z-Image Turbo. That low NFE count, just 8 steps to a high-quality image, plus the VRAM compatibility. It just means this model is actually ready for real-world applications where speed is everything. So to get that sub-second latency, what were the key software optimizations that really made the Turbo variant fly?
They really leveraged the state-of-the-art acceleration frameworks. So specifically, they used Flash Attention 3 for much faster attention computations, and Torch.compile to optimize the whole execution graph. That combination, applied to a model that's already compact and distilled, that's what gives you that accessibility we keep talking about.
Okay, so let's get into the architecture, because that's the foundation of the compactness, the Scalable Single-Stream Diffusion Transformer, or S3-DIT. For our listeners who are familiar with DITs, how is this design so much more parameter efficient?
The genius of S3-DIT is its unified single-stream approach. Most models have separate paths or different layers for different kinds of information. S3-DIT is modality agnostic. It processes all the tokens, text prompt, VAE image tokens, semantic tokens, all of it uniformly in the same transformer backbone. By forcing everything through the same 6 billion parameters, they just maximize parameter reuse.
And they built stability right into the transformer blocks themselves. Why was that so important? Were they solving a known instability problem that other big models just kind of ignored?
Oh, they were definitely solving known issues, particularly in very deep transformers where signal scaling can get really problematic. And that leads to instability during large-scale training. So they introduced 2 specific normalizations, QK norm and sandwich norm.
Okay.
CK norm, that regulates the attention maps, it stabilizes the query key interaction. And then sandwich norm constrains the overall signal amplitudes at the input and output of the attention and FFN layers. It just ensures a smoother gradient flow, which is not a trivial problem when you're scaling models this deep.
So they're essentially bulletproofing the transformer core. I also saw they engineered efficiency into the conditional injection mechanism itself. How did they cut down the overhead from the prompt conditioning?
Yeah, they moved away from using a full projection layer for the conditional info, which is super expensive computationally.
Right.
Instead, they used a low-rank decomposition strategy.
Help us visualize that. Are they just using like fewer, smaller matrices to handle the conditioning to make the model lighter without losing that guidance from a complex prompt?
That's exactly it. They use a shared layer-agnostic down projection, a small initial matrix for the condition, and then smaller layer-specific up projection layers. It dramatically reduces the parameter count needed for conditioning, which can be a major source of bloat in these big models.
So that's the architectural efficiency. Let's talk engineering, the distributed training. Because even a lean model can cost a fortune if the setup isn't perfectly optimized. How do they manage to stay within that $630,000 budget on the engineering side?
They used a really sophisticated hybrid parallelization strategy. For the small frozen components, the VAE, the text encoder, they just use standard data parallelism, or DP. But for the huge diffusion transformer itself, where you've got massive memory requirements for optimizer states, gradients, parameters, for that they used FSDP2, and that shards all that memory overhead across all the available GPUs.
And what other standard tricks did they use to squeeze every last bit of throughput out of those H800s?
Well, beyond just the parallelization, they use gradient checkpointing across all the DIT layers. This trades a tiny bit of computation cost for huge memory savings, which let them use larger batch sizes.
But wait, how standard is that at this specific scale? Were there any risks they had to mitigate there?
Gradient checkpointing itself is standard, yeah, but the clever part was how they implemented it for mixed resolution training. See, when you train with images of different sizes, you get a ton of padding waste. Your GPUs are basically processing empty tokens, which just kills your compute time. So they introduced what they call a sequence length-aware batch construction strategy.
So they're pre-estimating the token length from the resolution and then grouping similar image sizes together.
Yes, they minimize padding waste by grouping similar sequences. And they complemented this with dynamic batch sizing. So smaller batches for groups with long sequences, which avoids out-of-memory errors.
Yeah.
And then larger batches for the shorter sequences to really maximize GPU utilization. It's a very targeted optimization, and it's where a lot of other large-scale training efforts lose efficiency.
That is meticulous. Okay, let's move on. Section 3. Data. The Z-image team was very, very clear about avoiding synthetic data distillation. They argued it risks error accumulation, that homogenization that gives you that generic AI look. How did they get such high quality using purely real-world data and do it efficiently?
This is maybe my favorite part. It required building an entire efficient data infrastructure, starting with a data profiling engine. And this engine is all about quality density. It's about making sure every single piece of data is maximized for training value. It goes way beyond simple filtering.
What kind of features are we talking about here?
Multidimensional features.
Yeah.
So they use low-level image metadata, like ANSI Ouch for basic deduplication. But more importantly, they use sophisticated technical quality assessment to filter out images with low entropy, compression artifacts, that kind of thing. And this is critical. They trained a dedicated classifier specifically to detect and filter out AI-generated content. This is their secret weapon for preserving that physical realism and stopping the model from looking like everything else.
But scaling the deduplication for billions of cross-modal pairs, that must have been a huge bottleneck. How did they handle that?
That was the second major innovation in their data pipeline, the cross-modal vector engine. Traditional deduplication is just impossible at this scale, so they reformulated the problem as a graph-based community detection task using a super efficient GPU-accelerated k-nearest neighbor search.
So instead of comparing every single pair, they're clustering data based on similarity vectors, and then dense clusters are treated as like potential duplicates or semantic structures.
Exactly. They can process 1 billion items in about 8 hours on just 8 H800s. It's this massive scalability that let them maintain a hyper-clean, real-world data set while also extracting semantic structures they needed for balancing later on.
And this isn't just a one-and-done pipeline. It's improved by their active curation engine.
Yes. This human-in-the-loop cycle is absolutely vital. It's how they address those long-tail deficiencies concepts that are rare but really important for overall quality. The model gives feedback on what it struggles with, and that insight drives very targeted data annotation.
The cultural example they give is perfect. The squirrelfish, or assume case. A standard model might just try to literally combine a squirrel and a fish.
Right. And without this active learning, the model would probably fail on that concept forever. But the curation engine identifies the gap, and the system feeds it targeted, high-quality, verified data and captions to make sure the model understands it's a specific multi-step Chinese dish. That kind of focused correction is so much more efficient than just throwing 10 billion more random images at the problem.
Moving into the training curriculum, it runs from pre-training all the way through supervised fine-tuning, or SFT. In that SFT phase, where they're really pushing for peak quality, what did they do to avoid the common risk of catastrophic forgetting?
Catastrophic forgetting is a huge risk when you're fine-tuning a model. Their solution was concept balancing. They used that semantic graph we talked about from the data engine to identify underrepresented long-tail concepts. Then during mini-batch construction, they actively upweight those concepts to ensure semantic diversity is preserved. It stops the model from forgetting the rare stuff.
And they capped off SFT with model merging.
Yes, and that's a really smart final step. They train multiple SFT variants. Maybe one is biased towards photorealism, another towards instruction following. Then they just average the weights. This creates a final Pareto optimal model that's more robust across a huge range of prompts, and it neutralizes any biases from a single training run.
Now we'll get to the ultimate efficiency breakthrough. Few-step distillation. They had to take that 100 NFE high-quality SFT model and turn it into the 8 NFE Z-image turbo. We know standard distribution matching distillation, DMD, often creates artifacts. What were those artifacts and how did they fix them?
The artifacts were the usual suspects. Colors get washed out, you lose fine details when you compress 100 steps down into 8. Existing DMD relied on two main things: CFG augmentation, which speeds up convergence, and the distribution matching term, which stabilizes it.
And they realized those two parts were actually fighting each other.
Exactly. So their first fix was decouple DMD. They recognized that combining them was the problem, so they separated and individually optimized the CFG augmentation from the distribution matching regularization. This one change pretty much prevented all the visual degradation.
And their second innovation was DMDR, bringing reinforcement learning into the mix. Now, for our listeners, why is adding RL kind of dangerous, and how did they stabilize it?
Well, you add reinforcement learning to align the student model with human aesthetic preferences just to make the images look better, but RL has this huge risk of reward hacking. The model learns to gain the numerical reward score without actually delivering what a human wants. You get these really weird, unstable outputs.
So DMDR was their solution. They needed a leash.
And they use the distribution matching term as that leash. By integrating it alongside the RL optimization, they stop the model from wildly exploring and reward hacking. It ensures stability while still enhancing the aesthetics in the final turbo model.
But they didn't stop there. They added a final layer of polish with reinforcement learning with human feedback, or RLHF. This was a multi-stage process aligned by a multidimensional reward model covering aesthetics, instruction following, even AIGC detection.
Yeah, their RLHF approach was really focused on scalability for the preference data. So they used a two-stage strategy. Stage one used DPO, and it focused only on objective dimensions, things that are binary, verifiable. Like, is the text rendered correctly? Is the object count right?
So they're getting the easy, verifiable stuff right fast using AI helpers.
Precisely. They used VLM-generated preference pairs at a massive scale for these objective dimensions, and then just had a streamlined human verification step.
Yeah.
It massively increased their throughput for stage one.
And stage two used group relative policy optimization, or GRPO.
GRPO was for the online refinement. This is where they polished the subjective art. It uses a composite advantage function that aggregates all the scores from the reward model. This simultaneous optimization focused on subjective things: photorealism, aesthetics, semantic accuracy, and it was super effective at closing that gap between raw capability and what humans actually prefer.
Let's talk results, because this is the proof in the pudding. This is a 6 billion parameter open model, Z-image turbo, and its ELO-based human preference score of 1025 placed it fourth globally.
That's just a staggering efficiency to quality ratio. Not only did it rank first among all open source models, it actually outperformed several major closed source competitors. And the comparison against the 32 billion parameter FLUX2 dev model was stunning. Z-image got an 87.4% combined good plus same rate in a head-to-head. It just confirms they delivered elite quality at a fraction of the cost and size.
We have to circle back to text rendering, which you mentioned earlier. It's the Achilles heel for so many image generators.
It is. And Z-image made it a priority. They explicitly curated data that included OCR information in the captions using a chain of thought approach. And this hyper-focus paid off. They achieved a new state-of-the-art On the 1IG benchmark, hitting Buro 0.987 for English text and 0.988 for Chinese text. That robust bilingual capability is genuinely transformative for global applications.
Okay, finally, let's talk about the cognitive enhancements. If the core DIT is only 6 billion parameters, it's inherently going to have limits in complex reasoning and, world knowledge. They address this by decoupling that function into an external unit, the prompt enhancer, or PE.
The prompt enhancer is, I think, one of the most significant insights in this entire paper. It functions as an external cognitive unit. It's powered by a fixed, pre-trained VLM reasoning chain. And during SFT, the model is trained to align with the enriched, reasoned outputs from the PE.
So instead of trying to cram all of human knowledge into 6 billion parameters, they use the PE to translate a complicated, abstract prompt into detailed, step-by-step instructions for the generator.
Precisely. I mean, think about trying to translate raw geolocation coordinates like 30 degrees north, 120 degrees east into a specific scene like Westlake. The PE handles that translation. Or if you ask it for brewing pu'er tea, the PE injects the detailed sequential steps needed to illustrate that process. It provides a structured reasoning chain that the core DIT model just doesn't have on its own. This modular approach is what lets a small, efficient core model perform these complex, knowledge-intensive tasks.
That strategy is really how they make a small model punch so far above its weight. And that same efficiency and instruction following is seen in the Z image edit variant, which did great on benchmarks like imedit and gedit.
The whole Z image series, base, turbo, and edit, it really establishes a comprehensive and publicly available blueprint. It proves that you can combine a highly optimized compact architecture with meticulously curated real-world data and these advanced modular alignment techniques. This is the future of accessible, state-of-the-art generative models. You don't need infinite scale to get elite results anymore.
The cost is low, performance is high, and the accessibility for an open model of this quality is, well, it's unparalleled.
This paper demonstrates a really clear path forward for designing these efficient generative systems, where complex reasoning and world knowledge are explicitly decoupled and then injected using external VLM-powered modules like the prompt enhancer. And I think this raises a fundamental question for the entire field. Will future state-of-the-art models prioritize an efficient core architecture and just offload complex reasoning to external cognitive units, rather than trying to scale the diffusion transformer itself to hold all that knowledge?
That cognitive modularity argument is a powerful one. For all of you working in this space, you should note the Alibaba team has publicly released the code, the weights, and online demos on GitHub, ModelScope, and Hugging Face.
Go and take a look, because Z-Image really does set a completely new budget-conscious standard for what is computationally possible in T2I generation.